Welcome to the bonding unit. We're going to take a look at a few different types of bonds, and we're going to dive into one of those bonds in this video. So let's take a look first off at ionic bonds. It says ionic bonding are when electrons are exchanged. Okay, now it's important for us to understand that metals are losers. Okay, that meaning that metals are always going to lose electrons, and non-metals are, it says winners, but what are they going to win? Okay, I like to call non-metals gainers. Okay, because non-metals are going to gain electrons. So what's going to happen here is that our metal is going to lose its outermost electron. Okay, notice that you've got this little fella right here. You've got this one little electron here in its valence shell. So what chloride is going to do is it's going to steal that electron away from sodium. Okay, and so the sodium is going to readily give its electron over here to chlorine, and now chlorine is going to own that electron. So what happens now is sodium actually ends up with a positive charge. Okay, chlorine ends up with a negative charge. Well, what happens when you have a positive and a negative charge? Well, they love each other and they are going to attract. Okay, that is the basis behind an ionic bond. Okay, now compounds don't always want to give up their electrons all the way. So what's going to happen sometimes is that atoms are going to end up sharing electrons. So that's going to be the case in covalent compounds like water. Now, this is oftentimes going to happen when you have two nonmetals. Okay, so let's take water for example. I've got hydrogen, and oxygen. What's going to happen here is that these are going to end up sharing electrons. Okay, so now hydrogen is going to fill its valence shell with two electrons here, and this hydrogen is going to fill its shell with two. And oxygen over here now has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So everybody has a full valence shell to what they assume that their fullness should be. Okay, it's just that they're sharing the electrons. Where sodium lost an electron and chloride gained an electron, these little fellas here are going to share electrons. Now, metals do things very strangely, okay? It says metallic bonding, electrons live in a little sea of electrons. So we call this the electron C model, not the electron C model, the electron C model. Okay, so you can see all of our little electrons floating about within our metal. Now, we're not going to really focus on metal bonds, so you don't really have to worry too much about it. If you understand the electron C model, then you're going to understand everything that I need you to know about metallic bonding. Okay, so as promised, we are going to dive into the ionic bonding structure while we're in this video as well. As far as ionic bonding goes, this is going to look like a crystal lattice. Okay, its general structure is what's called a crystal lattice. And that's going to be where you're going to have a negative electron, positive electron, negative electron, positive electron, negative, positive, all through here. And it makes like a little cube type of structure. Okay, it's going to end up making a crystal when you have enough of them put together. It says electrons are transferred from one species to another. They're not shared. Okay, so generally, if you see a metal and a non-metal, that's going to give us an ionic bond. So here's some ways that we can predict if we're going to have an ionic compound. Okay, anytime you have a metal and a non-metal, we can predict that will form what we call an ionic bond. Okay. Also, remember how we memorized the polyatomic ions: nitrate, phosphate, chlorate, chlorite, perchlorate, permanganate, all of those fun things. Almost all of those polyatomic ions were negatively charged. Okay, so remember, a metal is a loser, meaning it's going to lose electrons and thus become a cation, which has a positive charge. So if a metal has a positive charge and we put that together with a negative polyatomic ion, that positive and negative is going to attract, thus forming an ionic bond. Okay, now remember, our only polyatomic ion that we had that was positive was ammonium. So if I mix that positive ammonium with a negatively charged atom, okay, which would be our nonmetals, because nonmetals are our gainers, then that's going to give us an ionic bond as well, okay? Or if I have an ammonium, which is a, excuse me, ammonium, which is a positively charged polyatomic ion with a negatively charged polyatomic ion, then we're going to have an ionic compound, okay? So the overall take-home idea here is a cation plus an anion, a positive ion plus a negative ion. Stick them together, and boom, we have an ionic compound. Now, the real way that you would tell if you have an ionic compound or not is based on what's called an electronegativity calculation, okay? The way that we would tell that is by doing this calculation, okay? We are going to calculate what we call the delta En, okay? Delta means change, En means electronegativity. So if I have a delta En of 1.7 or greater, then that means that the bond exhibits 50% or more ionic character, and we would definitely consider that compound to be ionic. So we need to remember something right here, okay? If we're predicting based on just what we have on the periodic table, okay, we would say that a metal, okay, remember our metals are over here. Oh, where am I at here? Okay, our metals plus a non-metal is going to give us an ionic compound, okay? So that's going to be our basic predictor, okay? Anything on the left-hand side of the stair-step line plus anything on the right-hand side of the stair-step line is going to give us an ionic compound. But if we want to be for real about it, then we would do the delta En. Okay, you're only on a test or quiz, you're only going to calculate the delta En if I ask you to. So let's take a look at a periodic table that has electronegativity values on it. Okay, so we're going to take a look in just a moment at that periodic table. But if I've got NaNCl, okay, let's take a look here. Sodium has an electronegativity value of 0.93. Actually, I don't like this one. All right, so let's take a look at this chart. If we want to look at the electronegativity values for sodium chloride, okay, sodium has an electronegativity value of 0.9, and chlorine has an electronegativity value of 3.0. So if I do 3.0 minus 0.9, that's going to give me an electronegativity value of 2.1. So now the question is 2.1 greater than 1.7? Yes, of course it is. So we would say that this indeed is ionic. Okay, let's look at BeI2, okay, beryllium iodide. So Be is right here, 1.6, iodine is 2.7. So 2.7 minus 1.6 would give me a delta En of 1.1. So now is 1.1 greater than or less than 1.7? Well, 1.1 is less than 1.7. So I would say that this is actually not ionic. So predict. Okay, so we'll just say not ionic for right now. Not ionic. All right, we're going to dive into a little bit more stuff here on the next video. But for right now, we'll just leave it right there. Thanks, folks.